All right, example 4, section 8.1. We're still in the process of discovering kind of a catalog of some parent polar curves. We've talked about circles that are off-center, that make a full rotation every pi units, and the diameter is the coefficient of the trig function. If we add a constant to the sine or cosines, we end up with a family of cardioids / limicons. And when the numbers are the same, we get a cardioid. When the constant is smaller than the coefficient, we get an inner loop called a limicon. And when the constant is bigger than the coefficient, we get something called a dimpled limicon or dimpled cardioid. Anything that had cosine had x-axis or polar axis symmetry. Anything that had sine had y-axis symmetry or symmetry with respect to the line theta equals pi halves. Okay, so now we're looking at these. These kind of look more like the first ones we did. There's only one term, but instead of just 3 cosine of 1 theta, it's now 3 cosine of 3 theta, 2 cosine of 5 theta. So what we're doing is we're taking the angle theta and we're changing the value in front of it by some factor. It's not just 1. Now, instead of sketching these by doing a table of values, because it's going to get kind of tricky because we have to choose values from the unit circle, and then so that when we triple them, we recognize them. So let's just go to the calculator. We'll just do a couple of these. I think y'all will pick up on the pattern without having to do all of them. Switch to polar mode, and also make sure you're in radian mode. I did a problem last period in AB, and I was in degree mode, and I didn't see the graph because I was still in pre-cal thinking. But we should always be in radian mode. So let's go to y equals, and we'll type in our function now. R equals 3 cosine of 3 theta. So again, if you hit zoom 6, it's going to give you your negative 10 to 10 window, but it's also going to graph your theta from 0 to 2 pi, which should be fine. So here we go, zoom 6. Whoa, that was fast. That was so fast. Let's slow it down. Go to your window, slow it down. How about 0.005? Let's see if that works. Notice where it starts and how it's traced out. And notice it's still working. My calculator's still graphing, but you're not seeing anything, and now it's done. So this one started over here on the positive x-axis, and it passed through the pole, looped around, passed through the pole a second time, looped around, passed through the pole the third time, landed over here. And that looked like it was from 0 to pi, because as it was still graphing, it looked like it traced over itself again. So let's see if that's true. We could change the upper bound from 2 pi to just regular pi and hit graph and see what happens. First pole, second pole, third pole, and it stops. There you go. So this looks like a balloon animal, right, that you'd maybe get at a circus. But if you graphed it in a standard window, watch this. Zoom 5 is a square window. And what it does is it makes the x-axis a little bit longer than the y-axis because the proportion horizontal. This actually does have rotational symmetry. Some kind of rotational symmetry. Not origin symmetry, but it looks kind of like a propeller, right? And the propeller would be bolted down at the center, which is the origin. The graph itself has x-axis symmetry, which maybe you would suspect because it had cosine in it. We actually call this graph a balloon graph would be great. Let's see if we can transfer it over here. It starts over here at the point 30. All right, 30. And it comes in like that. It makes one over here, makes one over there, comes back over there. And they're all supposed to be symmetric, but mine aren't. We call this a rose curve. You asked about the rose yesterday. This is what we call the rose curve. This one has 3 petals. And what's the length of each petal? 3. Okay, so 3, we'll call it the petal length. Is 3. And it traced out once from 0 to pi. And of course it has x-axis symmetry. Now, 3 petals and a petal length of 3. Do you see any 3's in the equation? Yeah. I see 2 of them. I have 2 different 3's over here, 2 in the equation. Do you think there's a coinkydink? Yeah. Which 3 in the equation do you think was responsible for the petal length? The coefficient of theta or the coefficient of cosine? cosine. Yeah, and it makes sense if you go ahead and graph it by facing due east. When theta is 0, plug in a 0 for theta. You get 0 times 3 is 0. Cosine of 0 is 1. And now 1 times that 3 in front tells us how far out we go. So the number in front will tell you the petal length. Petal length. And I guess the other 3 tells you what? Yeah, how many petals, or the number of petals. All right. So with that in mind, what do you anticipate this one to be? 2, 5. How many petals will it have? 5 is the right answer. And what's the length of each petal? 2. And it should trace out from 0 to pi again. Let's just verify. We'll change it to cosine of 5. All right, here we go. There you go. And it's perfectly, each one of them is perfectly symmetrical. Trace out from 0 to pi. All right, the next one. What do you think this one's going to be? How many petals? 7. What's the petal length? 4. Traces out once from 0 to pi. Has what type of symmetry? X-axis. Yeah. So let's graph it. They start getting really hard to draw by hand, at least if you're trying to make them pretty, perfectly symmetrical. But the calculator does a fine job of it. So 4 cosine of 7. Ooh, ah, ooh, ah, ooh, ah. Pretty, right? So again, notice, does this graph pass the vertical forearm test? No. So it's not a function of x, right? So if we were trying to write the rectangular equation for that, oh my gosh, that'd be some big looking ripped equation, yeah. But if you look at it in polar form, it's like, oh, it's that. That's relatively simple. What? You can, which gets me to my next observation. What have you noticed about the coefficient of theta in these 3 examples? They're all odd, okay? Let's stick with odd for a second. If I simply switch from cosine to sine, what you think happens? Nice. Yeah, it's going to have the same behavior, 3 petals, petal length of 3, but with y-axis symmetry. Okay? Same thing here. Petal length of 2, 5 petals, y-axis symmetry. Petal length of 4, 7 petals, y-axis symmetry. Let's do this one and this one only. I'm just going to come over here and change cosine to sine. But as Peter noticed, and as probably you noticed, we still are talking about odd number of petals. Okay, and that one has y-axis symmetry. Y-axis symmetry, x-axis symmetry, still traces out from 0 to pi. All right? So let us summarize very quickly here. What do you notice about the graphs? Number 1, they trace out from 0 to pi. And if they're of the form y equals a, we'll say sine, let's do this. Do them separately. A sine of b theta and y equals a cosine of b theta. They're going to have b petals, and a is the petal length. And of course, the sine has y-axis symmetry, and the cosine has x-axis symmetry. But yes, let's make one note here. We have b petals, and b has been an odd number. What happens now if we let it change to an even number? You've already tried it, or you're guessing? Good. Okay. So on example 5, if we have 3 cosine of 2 theta, well, you would probably imagine it having what type of symmetry? X. It would have a petal length of what? 3, and you might suspect 2 petals, but you'd be wrong if you graph it. And notice I still have my window from 0 to pi, yeah? Because the others made a full loop in pi. If I leave it at that, Do I even get a closed loop? No. So if I went back now and I changed it to 2 pi, which is what it was by default, that's once around the unit circle. Now I hit graph. I'll get everything I got before from 0 to pi, but look what's going to happen. It's going to then trace out a symmetrical second half, and now it's stopped. It stopped graphing. So now you see not 2 petals, but 4, and now it also traced out twice as many petals, but it took twice as long, yeah? You can, yeah, and you can give them to your girlfriend. Sure, yeah. Here's some geeky math flowers. Be mine. All right, so with this one here, very quickly, what would you suspect? What type of symmetry? X-axis, how many petals? 8, traced out from 0 to 2 pi and a petal length of 2. You'd be correct. This one here, how many petals? 12. Good. So as it turns out, if let's say this right here, if B is an odd number, okay, in the form y equals a sine or cosine, it doesn't matter, of B theta, if B is odd, you're going to see B petals. And it's going to trace out from 0 to pi. If B is even, you're going to see 2B petals, and it's going to trace out from 0 to 2 pi. Yeah, you could almost think of it in terms of both of them in terms of 2 pi. When B was odd, you remember the first time we did it from 0 to 2 pi. It traced it out 3 petals, and then it traced over the exact same 3 petals from 0 to 2 pi. So you can kind of think of that as also being twice as many petals. It's just that the other 3 that it graphed were on top of the first 3, so you didn't see them. Whereas if B is an even number, the other set that you see traced out traces out in a new place, so you actually do see them. So it actually visually appears twice as many petals from 0 to 2 pi. Okay, so kind of interesting. I would just memorize this. If B is odd, you see that many petals from 0 to pi, and if B is even, you see twice as many petals, and it takes twice as long to trace it out. And those are called rose curves. So you can kind of play with it. You could do like 23 petals if you want, 24 petals, whatever you want. And it gets kind of crammed in there. And if you graph one on top of the other in a different color, oh my gosh, artwork. Okay? So those are really the kind of family of parent polar functions that you need to at least be familiar with. You have the offset circles, you have the cardioids, limicons, and then you have the rose curves. Now, there are a couple. Let's look at a couple of exceptions. There's all kinds of classifications. What if I just had something like theta equals pi halves? I've already kind of mentioned that. What would that look like? You can't graph that on your calculator because your calculator, it has to be solved for r. But let's think about it. In rectangular form, if I just had like x equals 4 and there was no other variable called y, then we know that y, if it's not in the equation, could be anything as long as x is what? 4. So we would graph this like this. We'd go over to x equals 4, and we can let y then become anything. So we put a bunch of dots, and then we draw a line connecting them. So it would be a vertical line. Same thing here in polar equations. If there is a radius missing, then the radius could be anything. Positive, negative, 0, as long as the angle is what? Pi halves. So let's go rotate up to pi halves. We're pointing in this direction. And let's let the radius be 0, 1, 2, 3, 4. How about -1, -2, -3, -4? Connect the dots. What do we get? A vertical line. So theta equals pi halves is also known as the y-axis. It's the same as the equation x equals 0. So that's why when we say it's symmetric to the y-axis, it's the same as saying it's symmetric to the line theta equals pi halves. And one other one here. What if I have just something like r equals 3? What would that look like? This one you could graph on the calculator because it's solved for r. But now if there's no theta, that means theta could be anything as long as the radius is what? 3. So come out 3 units, and then let the theta be anything as long as you're 3 units from the center. What do we call that shape? A circle. Now that's going to be a circle whose radius is 3, centered at the origin. That's different from the circles we first saw where they were offset. Okay? So if you just have r equals, it's a circle centered at the origin. If you just have theta equals, it's going to be a vertical line. And then here's a cool one. What if you just have r equals theta? That'd be kind of like y equals x. Is that a line? Which one is our independent variable? Theta. So as I rotate from 0 to 2 pi, from 2 pi to 4 pi, 4 pi to 6 pi, what's happening to my radius as theta gets bigger? A swirl or a spiral. They could spiral. There are Fibonacci spirals, yeah. And if you could write it in polar form. So well, it stops because your theta min and max is set to 0 and 2 pi. If you set your theta min to like negative 22 pi and your theta max to like 1 billion pi, it'll keep going, all right? Your calculator graphs it in a finite interval for theta, all right? But you can expand it. So that's a spiral. Okay, so we're still not quite at the calculus part. We want to now convert from polar to rectangular coordinates and equations. And we did that a little bit at the beginning yesterday. So the xy is your rectangular coordinate, and r theta is your polar coordinate. So if you're converting from polar to rectangular, that means you have r theta in hand, and you're trying to convert it to rectangular. We did this yesterday. You're going to use x equals r cosine theta, and x equal or y equals r sine of theta. Those are like your component vectors from physics. Okay? You just plug them in and evaluate it, and you're done. If you are converting from rectangular to polar, that means you have your x and y coordinate in hand, and you're trying to convert it to a particular polar coordinate. Then, of course, the radius is x squared plus y squared square root of. That's the hypotenuse, the Pythagorean theorem. And we typically use tangent because it has y and x in it, and we'll solve that for theta. All right, so let's try it out. Convert the following coordinates as specified. Convert 2, 5 pi 6 to rectangular coordinates. So this must be an r, and that must be a theta. So remember, how many rectangular coordinates are there for any given polar coordinate? To navigate to any point in rectangular space, there's only one way to get there. Okay? For polars, there's infinitely many. So there will be one x value and one y value. So the rectangular equivalent xy is going to be 2 cosine of 5 pi 6, r cosine theta, and 2 sine of 5 pi 6. And all you have to do is simplify that. So what is cosine of 5 pi 6? Unit circle time. Negative square root of 3 over 2. Good. So you might want to review the unit circle. We're going to be using the unit circle quite a bit in this polar section, as you can imagine. And then sine of 5 pi 6. Second time today we've seen it. It's a half. So this ends up being negative square root of 3, comma 1. And let's go ahead and plot that one just so we can kind of remember how to do it. We're going to rotate over to 5 pi 6, which is over here. We're pointing in that direction. And we're going to march out 2 units. So 1, 2, somewhere in there. And now we're saying you could also get there by going left square root of 3 and up 1. Okay, makes sense. All right, we're going to work one example each way. Now I'm converting 3, negative 3 to polar coordinates. So now I have an x and y. Let's go ahead and plot that point. 3, negative 3. It's like we're back in 6th grade or something. There it is. We plotted a whole sheet of them. We connected them, and it made like a Martian or something. Remember that when you're first learning the coordinate grid? Fun. I know. Now we want to convert that to polar. So let's go ahead and find the radius first. The radius, remember, is the square root of x squared plus y squared, hypotenuse. So that's going to be 9. What's negative 3 squared? Also 9. Good. So that's going to be the square root of 18, which is, simplifies to 3 root 2. Good. So there's the radius. And now I want to figure out the angle. So tangent of theta is y over x, which means it's negative 3 over 3, which is negative 1. And now it's unit circle time, or time circle unit, in reverse. Where is tangent equal to negative 1 on the unit circle? Yeah, at 3 pi fourths or 7 pi fourths. Now, we have to be careful with the angle, remember, because ultimately I can combine any pi fourths reference angle with a positive or a negative radius to get to that same point. So we kind of have to put the pieces together. If I call that my terminal ray, I can either call that negative pi fourths or I can call it 7 pi fourths, whichever one you want. And if I'm pointing then in the direction of that ordered pair, my radius will be what? Positive or negative? If I'm pointing in the direction of the ordered pair I want to get to, my radius is positive. Good. So in the form, remember, r theta, my radius was, what, 3 square root of 2? So it could be 3 square root of 2, 7 pi fourths. Or it could be 3 square root of 2, negative pi fourths. So that would be the 2 within one rotation. And then I can also, if I prefer, I can get to the opposite terminal ray. That would be a negative 3 pi fourths and a positive, that would be a positive 3 pi fourths and a negative 5 pi fourths. So I could also do those, but then what would my radius be? Negative, yeah. So I can have a negative 3 square root of 2 and a 3 pi fourths. And then the last one here, might as well just finish it out. Negative 3 square root of 2, negative 5 pi fourths. Running out of room. So within any one rotation, positive or negative, you're going to have 4 solutions, one each with a positive, negative radius. And of course, infinitely many more. All right, so that's converting actual ordered pairs. We now want to convert actual equations, and we won't maybe get through all of these. So the line 2x plus 1 in rectangular form has a polar equivalent. How in the heck are we going to figure out what the polar equivalent is to this rectangular equation that we know so well? What can I use? I want to get rid of the x and y and somehow introduce equivalently an r and or a theta. Would that work? Yeah, I would plug it in, substitute. So y is equal to r sine of theta, and x is equal to r cosine theta. See that? Now, typically, we like to solve for r, don't we, in polar form? So once you replace it in terms of x or theta and r, try to solve for r. Okay, some things may not be able to solve for r, like we can't always solve for y. If you do this, we're going to get everything on one side. We get r sine of theta minus 2r cosine of theta, and that equals 1. And now I can factor out an r. And that leaves me sine of theta minus 2 cosine of theta equals 1. And now I can solve for r. I go 1 over sine of theta minus 2 cosine of theta. And here's a perfect illustration. Remember that in general, polar curves can accommodate elaborate curves a lot more easily, and rectangular equations can accommodate less elaborate curves. The rectangular equation for a straight line in this case is pretty straightforward, and now the polar equation for that straight line is just a little bit more bulky. And we'll graph that when you get back from lunch on the calculator. It's kind of neat how it sketches the line. It's not like you would imagine, unless you imagine it correctly.